Chin and Co and Robert Welsh from Arista and Nevion, they're going to come up and we'll bring up the slides. I think we're on the first slide, and we'll go right into it. So,
okay, how are we all doing? Good. All right. We were going to do Turkey, but tryptophan doesn't really work when you're doing presentations, so we switched it up a little bit. So I'd like to introduce Chin. Actually, we're going to announce something else here. First off, so for those that didn't know, we actually announced today. Thank you, Luann, for doing all this. A development agreement between Arista and Nevion. This is something we've been working for the last, years? Yeah, a long time. And we finally got it to actually do something. We're going to share with you some ideas that we have around that, but more importantly, we want to get your involvement in this. We want to hear what you guys think about what we're doing from a networking perspective, what we're doing from a contribution perspective, from a broadcast perspective. So we want to make sure this is interactive. Now, I talk way too fast, so I'll slow down a bit. But I want to introduce a really good friend of mine, Chin, who is, what do you have 2 PhDs?
No,
Is it?
what?
Yes, he's very smart.
You're just making things up at this point.
Yeah, so making things up at this point. Really smart guy on contribution things. He and I go back and forth on the whole presentation. We want to talk about some interesting ideas and get your feedback. So we're going to talk about an example of a broadcast communication, what do we call it, a new facility.
You're
right. Okay.
So what we want to talk about is actually a real life case study that we've deployed back in 2017. And it's actually an Intra and inter-facility IP production network. So it's not just an in-facility network, but it's a combination of an in-facility. It's actually 2 separate facilities, one in Oslo and one in Bergen. And it was built for TV2. So TV2 is the largest commercial broadcaster in Norway. And their primary content is all news and sports. So their workflow, they've seen that it's been evolving and it's moving more towards a kind of like an over-the-top delivery. So back in 2017, they had a huge mandate to reduce the cost, both operational and capital costs. And of course, one of the most one of the heaviest burdens is of course the buildings itself, the lease, the amount of property that you have to own. So their mandate was to cut the sizes of the facilities and the number of staff that was actually that they used to deploy and do their production by a pretty large amount. So they had a set time. In August of 2017, this was back in January of 2017, they had a set time where they had to move facility, and there was no negotiation about that. Their lease had run out, they'll be kicked out of the facility. And 4 months later, they have to shift their facilities in Oslo at the same time. So they outlined their basic requirements. So of course, reduction in OpEx, right? But they also wanted to see whether they can avoid any build out in terms of SDI infrastructure. Can you go all IP? They tried, but there were a lot of components that were still baseband, so you had to account for that. But one of their stated goals was to achieve some form of platform flexibility. Now, at that time, they didn't realize what it meant. They just wanted an environment where they can reuse resources and share these resources on demand, regardless of the distance. So that was their primary mandate. And the real reason why they needed to do so, because of the layout of their systems, right? So they have production that's run in both cities, in Bergen and in Oslo. And they already had a WAN circuit between these 2 cities. The WAN circuit in this environment was dual 100 gig circuits, and they wanted to leverage that high capacity bandwidth to actually do remote.
We've got hecklers already.
I'm being heckled. So their main facility was in Bergen, but they also ran a lot of production in Oslo itself, and they thought about, hey, can I actually make my resources dynamic to the point that I can actually have a control room in one city running a live production in another city itself? So that was their stated goal. Now, in the build out into that environment, they had to make some fundamental choices. The first was that they actually had to select a project lead in this case. So because the move was very fundamental in the sense that they wanted to change the entire architecture of how they distributed content, the lead was actually the orchestration provider. Now, in this case, that's us. But Nevion also provided the switch fabric itself. So some of the other things that they considered were what kind of architecture actually is the best fit for their environment. So What they went with was a distributed spine leaf topology, fully redundant, primarily because their facility isn't a very large or massive one, but they want it to be as distributed as possible. So the other thing that they wanted is a software-defined network. So in a truer sense, they want the ability to actually, from a centralized management system, be able to do routing, traffic management on the fly across the two LAN facilities and across the WAN itself. So they didn't want separate management, separate orchestration system. They wanted their users to go in through one user interface and be able to manage all their connections regardless of where they are physically located.
So I think this is an interesting point because they were looking at this, well, what are we doing now? And then they didn't know where things were going to go in the future. So they're trying to, and everybody puts the air quotes around future proof. We all know that's, how much can you do? You throw kind of the lawn dart and you go, that's where I want to be. But that's literally what they were trying to do. And they were looking like the facilities as a big hybrid facility as if it was just one. So they wanted to control this as much as they could, IP and SDI wise, onboard the things that they had, move the things they could, but be ready for the future. And this is a hard thing for people to do because talk about retool, retrain on the fly with a mandate, a timeline. So these guys were under the gun to try to figure all this stuff out, and they pulled a bunch of people together to figure out basically the best brains in the business, and talking to all the SMPTE guys and saying, what do we do? What really works? What doesn't work? And is this 2110 really going to be something we can bet on? And they're putting their careers on the line for this stuff. So we'll talk a little bit more, and we'll go into each one of these, by the way, a lot more detail. And if you have any questions, feel free to speak up. Any questions online as well.
Okay. So when it came to the actual distribution, the encapsulation piece, this was back in August 2017. They made the decision in January, right? So from a standards perspective, they knew they weren't really ready for it, especially since 2110 wasn't actually ratified as a standard, right? So they took the hard choice and said, okay, I need to move right now. I have no other options. What can I do? But you still try to leverage some sense of COTS deployment within the network itself for the switch fabric. So they went with TR04. So this is just a slide to say, look, from a standards perspective, all these are really great technologies. It wasn't available at that point. We were even considering the use of ISO 4 and ISO 5 for registration, discovery, and control. But again, working with so many vendors and expecting all the vendors to support it simultaneously was a very, very difficult element for them. So what we went with is it's kind of a hybrid. And we'll talk a bit later about that because what they end up doing was building drivers for certain endpoints, but leaving the other endpoints as statically configured devices so they can switch it on the fly.
So hang on just a second here. Who's new to 2110? It's okay, we're not trying to embarrass you. Okay, Rick is. You never heard of it before? Okay, so do you guys know the difference between, and gals, know the difference between 2022.6 and 2110s? Okay, so 2022.6, think of like you're taking your SDI cable and you put it into IP and you gateway it. So everything comes across that. You got your video, audio, ancillary data, your VANC stuff, it comes right across. 2110, instead of being one stream, if you want, one pipe, we're actually taking video, audios, ancillary data, and we're splitting them across. So each one of these are different essence streams. So it makes it a little bit more complex. And for these guys to actually just say, we're going to go IP, this is more than just J2K and MPEG encoding. If we're going to go IP, what does that really mean? And so they had to get their arms around what does it mean to go IP first. So starting off with 2022-6 is a good way to get kind of your feet wet without having to worry about alignment, when things are going to actually be timed right, whether the gateways are doing separate video, audio, ancillary data. So this was a good way for them to actually get into this. And that's what we're seeing most times is people actually start testing out. I think you guys are doing the same thing with 2022-6. The 2110, as you can see here, you got the -10, which is kind of the overall dock. And then we literally say video, audio, ancillary data. Actually, it's the 20, 30s, and 40. And that's literally how it's split out. Now, the interesting thing about this is now you can pick and choose. I could say I want audio from this guy and I want audio from this guy, and you can have it totally separate and you just get that traffic. Or you can say video primary and video secondary. So it gives you choice. Choice means also in some ways complexity, right? With choice and complexity, but also it gives you the ability to actually only pick and choose what you want. I don't want this video, I want that video, okay? So it actually gives you the good stuff. Then NMOS, we've got Brad in the room, Mr. NMOS. So we actually have Mr. SMPTE and Mr. NMOS in the room, which is, I hope the room doesn't blow up or something happens or the food causes something else, issues, because then we would all be out. So the ISOs, if you will, we have registration discovery. We'll go through that a little bit more, 5, 6, and 7. The 4 and 5s right now, we'll talk a little bit more about that. Those are the ones you want to focus in on. Those are the ones that you actually care about most. Now, I'll be honest, who's in the room that's going to be writing an RFP? Nobody? Okay, good. All right, go ahead and put these in the RFP then. Nobody's going to be writing it. Okay, and there you go. Speaking of ISO 4 and 5. So everybody has a printer at home or something like that, right? They have something they actually print to at home. And when you plug your PC into the network that has a printer, you can find your printer. It's called a Bonjour protocol. We want to use that same type of cloud principle, you know, the new stuff, if you will. So when you plug a camera in and it's on stage 3, camera 2 in stage 3, we know where it's plugged in. We know it's camera 2. We know it's plugged in at stage 3. And it registers, it knows it's an HD cam, right? We know all the functionality around that. That's literally what this is. If you could click it real quick. Okay, click it. I get to click it. What happens, we have a registration and discovery service, what we call an RDS. So from a RDS perspective, we get the information about all the devices that are out there on the network. What this now gives us is the ability to control this. We know about it, we have the ability to control it. If it doesn't register, we don't know about it, or you have to manually put it into the system. This gives us our IP address, the device type, all the information we need to actually give it to a control system, now control it. If you think about what we're doing today from an SDI world, what do? We have an input, we have an output. And we get some type of intern, and hopefully they don't mess it up. They go, give me all the information around this, right? And then when you move it, you have to change your matrix. We want that to be more dynamic. We want to use new IT principles for registration discovery to know where things are, dynamically set it up. And then also, and also more importantly, quite frankly, if this thing goes offline, I want to know it went offline or if it moved. Right? So that's the new IT principles. We were talking about storage here just a minute ago. What we're finding is that you have more bandwidth from a networking perspective at the edge. The new Macs that are coming out, Thunderbolt 3, 40 gigabits, 40 gigs of throughput at the edge. I know, it's a lot. So what you have to do is you have to beef up your network in order to handle these things. So you might gateway them with like a Sonnet Echo Express or an auto device to actually do interesting things. From a workflow perspective, we're finding, like I'm working with the Marvels, the ABCs, the Universals, all those guys, they're bringing content in. But you can't bring it in. You can't put it onto your MAM system until you bring it over the network. If you only have a 1 gig link here, you're not going to put it on the MAM. You're going to actually bring it out the edge. All the workflow is going to happen here until you actually finalize it and put your final copies here. So what we're doing is we're seeing that this new paradigm is taking use of higher bandwidth, 40 gig, 50 gig, 100 gig, all the way out the edge. 100 gig to the edge, we're seeing a lot of. So it's interesting. It's a whole new world out there, big bandwidth. Is that making sense, you guys? Okay, am I talking too fast? Is it good? So from bandwidth, we get to control. So with all that bandwidth, you have to have control.
So it came a point where they had to actually define what their network architecture will look like, right? So they have many choices. I mean, these are just a small subset of it. We can do the centralized style, a large monolithic router, a large multi-slot router, connect all your endpoints to the routers directly, or even go into like a pseudo star where you have a pure XY separation or AB separation on the network. But what they eventually went with was a true spine leaf. Now, the actual deployment itself made use of 100 gig top of rack switches, but these top of rack switches can be a large modular switch too, or spine switch. And in some cases, in some of our applications, we're actually looking at a centralized super spine architecture, where you actually have a spine leaf in a larger network, in a larger remote location, but have large modular switches that act as your super spine in your data center.
So if you look at this from a networking perspective, just make the packets move. This is not real time. Your packets don't move this slow. They move in nanoseconds. Okay, so So we're talking about spine leaf versus monolithic switch, okay? In a monolithic switch, you'll have a bunch of line cards, and really it's spine leaf internally, quite frankly. There's a lot of math that goes on if you have to think about these as tie lines, right, from a spine to a leaf. And we're all used to tie lines and doing tie line management, right? So you have to figure out the bandwidth here. Well, without a controller, or you're doing these things called IGMP joins, you're trying to make sure that you have enough bandwidth, you don't have any collisions. If you don't have enough bandwidth, what ends up happening is everybody suffers, right? Things get backed up. So it's not just you and your stream, it's everybody else behind you. It's like the last person out the door. You've got to wait for them to get out the door before you can too. With a modular switch, everything's non-blocking. Now, can you pick and choose and mix these guys together? Sure, absolutely. And that's what we want you to do. Is we want you to think about what's your total bandwidth on this, okay? So the interesting thing is it's a cumulative. You can never have too much, by the way. And we'll get into that in just a little bit too. Moore's law is really taking effect. We're talking about 100 gig, but we're going to talk about 400 gig in the next couple of slides.
So to Robert's point, so to run a pure spine leaf fully connected network, one of the reasons why you would do this is because you want to distribute your load, right? So in most deployments, there are actually some suggestions out there that says that any input can hit any output. So in a truly distributed environment where you want to have non-blocking, it's really not possible, right? Especially if you try to scale it horizontally. So this is where the broadcast controller or SDN orchestration comes into play, because the orchestration system actually needs to know what are available bandwidth or links that goes out from the leaf to the spine switches, but also what's already exists on it and what's reserved in advance, right? So you can run this in a small environment, but it doesn't really scale out if you don't have the correct orchestration system on top of that.
You know, what's also interesting is just staying on the slide is people talk about blue and green, separate networks. And I get this all the time. I want to air gap these guys. I want to air gap that. I want to have two complete networks. I'm like, okay, my sales guys will sell you two, but do you need to, right? What if you actually connected the blue and green together and you had resiliency, you had failover? So if Chin's sending me a packet, a stream, if you will, and I happen to drop off and we send it to somebody else and he doesn't change, that's a good thing. So he's still sending the same content. So we're talking through this quite a bit where we're, you know, in some cases actually mixing blue and green. Now there are mandates that go, nope, I need complete separate because I don't trust it, and we'll work with you on that too. So it's all up to you. So you have choice. That's the thing.
Okay, so some of the challenges that we in running this environment is that this is a mixed vendor environment. So TV2's mandate is, let's bring best of breed. Let's not focus on only one vendor, but let's look at all the players and see who can come in with the best solution, overall solution. So it's a mixed vendor environment with its own problems, of course. In terms of control systems, there were actually 3 control systems in play. All right, and in Europe, VSM is very popular. So it's a broadcast control interface. All the operators are very familiar with it, so you don't really want to take away that user interface from them. So that is the actual first stage interface for any human operator that sits out there that wants to make a connection. But it in turn talks to the orchestration system, in this case video iPath, that actually is the SDN orchestration tool that builds the connections in the switch network in a very dynamic fashion. There is a third control system, actually a more monitoring tool, and that's data miner. So for overall monitoring over all the endpoints and devices in the network itself. So of course, back in 2017, when we started deploying this, you know, we try to make the best case scenario that everyone can deploy with varying degrees of support for PTP. And it was an uphill challenge, I can tell you that. But they got it up, they got it running, it works. But even at this point, 1 year later, we are still looking at the overall design and trying to figure out if this is the best PTP distribution method.
Well, let's hang on. I think we kind of talked about this, but PTP and having PTP in the network is very, very important. In fact, we were talking about the video, audio, and ancillary data. All those are timed through PTP. It's kind of like if you try to run your facility without Blackburst, you know, everybody's kind of free running on their own. So PTP is kind of that beat of the drum that everybody dances to. And if you have different, it's kind of like when I'm dancing and people try to get next to me, they get all out of whack, right? But so, okay, maybe that's just me. It's like an 80s dance. But PTP is the most important protocol to make sure everything is in sync.
Right. So So of course they had to make use of existing equipment, right? So they had Sony cameras, they had a Aspen playout system that needed to function. So it was all brought into the network. What was really difficult was because the actual pace of evolution itself. So not all the vendors were progressing at the same pace. We do a initial release, we deploy all the systems, then we find problems. Vendors come in, oh, by the way, you need to use this latest firmware upgrade. Just trying to organize that was
a challenge.
Yeah, that's putting it very lightly.
Okay, yeah.
But it's one of those things that we need to do in order to advance the whole, I guess the whole group or the whole industry, right? Everyone needs to kind of like keep up, play to standards, and operate at the same level. So the actual signal flows in the system. So the network itself was it's an SDN network. It's entirely controlled by the orchestration tool. We had a PTP grandmasters and 2 grandmasters in Oslo, 2 grandmasters in Bergen, all locked to GPS. There were still quite a number of SDI components, and in those cases, we actually had to do gateways. So the gateways were provided by third-party vendors or by Navion. But there were quite a bit of native IP interfaces too. I think in this example, the most efficient use case is actually using the GV node as a multi-viewer, creating another -6 stream and sending out as a -6 stream to an Embryonics SFP to a monitor wall, right? So it's
wait, say that again? Huh? You went in from where to out to where to?
So video streams will be coming from different gateways, go into a GV node to create a multi-view, out as -6 into the network and out to a Embryonics SFP.
By the way, when we're doing all these interops and things, when you're going from SDI to IP to SDI to IP and back and around, this is painful. I'll be honest, because it's painful enough just going SDI and tie lines and things like that. Now add in IP and all the mixes and go. So if you're going to go to IP, run, don't walk to IP. Seriously, because otherwise you're going to have IP addresses, SDIs, and all kinds of stuff, and you could have situations where you're trying to join into something that you've already just sent out and contributed. So it's a spreadsheet challenge. Right? It's almost like a 6-sided Rubik's cube sometimes. Okay. I'm just saying. Oh, this is not being recorded, is it? Oh.
So in addition to that, they also had a ton of signals that came from satellites that needed to be converted. So this network itself is not pure uncompressed. There's also transport streams within the system itself, both from satellite feeds and from using JPEG 2000 to send content between the 2 facilities itself. So that needed to be managed simultaneously. So if a user said, I want to take content from Oslo and bring it to Bergen, it may go uncompressed, but if there's insufficient bandwidth, the system actually takes in an account, runs JPEG 2000 and sends the content over there. So it all appears seamless to the user.
So PTP, we mentioned this, is very important. It is the most important protocol to do the video, audio, and ancillary data, to pull all 3 of those together. It's the timing mechanism. We know exactly where the frame is. We know where the startup frame is. We know exactly what the details are associated with this. Now, the hard part with this, though, is if you have multiple transmitters, multiple receivers, and you're trying to synchronize all that, this is the only way to do it across a network. PTP is a multicast, what they call multicast. And I'll get into that in a second. So your considerations are this. By the way, who's new to PTP so I can pick on them? Oh, so nobody's going to raise their hand now. Okay, same guy over here. Good, we'll pick on him. Come on, everybody. So it's called, and I got to stand back here because when I say this, sometimes I hit the whole room. It's called Precision Time Protocol. Okay, now they know why I stood back. So in Precision Time Protocol, what we're trying to do is to make sure everything is in sync. Okay. So much like with Blackburst and DAs, we're actually sending out pulses. And the pulses are per something called the 2059-2 spec, ST2059-2. Read it, it'll put you faster to sleep than I do, okay? I mean, it's that terse. So we have something called a PTP Grandmaster. We have a couple of those, and we actually prioritize them. We set them by a priority. If he's gonna have a higher number, I'll have a lower number. He becomes priority over me. And so we'll have something called a BMCA, Best Master Clock Algorithm. It's a mouthful. BMCA is easier to say. And we'll figure out who across the network we're supposed to align to. The cool thing, though, is you could make your switches look like a DA. So instead of every one of the devices going back to the PTP Grandmaster, you just go to the local switch. What does that mean? We could talk to your Tektronix guys. They can go into great detail about this. That means you get economies of scale on your SPG 8000As on your Tektronix, right? That you can analyze through your Prism. Yeah, there you go. I want my $2 now. Okay. Right now. There's $1. Okay, it just went down. So you got your SPG 8000As, you got your priority set, and everything is clocked across the network here, okay? So what's interesting about this is, and watch the greens and the yellows there, is when you actually change your grandmasters, the local switch doesn't change. It stays stable. Just follow the arrows. So all that changes is the grandmaster and then the spines up north. So what this gives you is now more resiliency. Even if these fell offline, let's just say, it was a really bad day, and both SPG 8000As with your Prism analysis went offline. Well, then you're actually in free running, and the clocks are actually still in sync because the whole network is in sync. So the switches become a part of your PTP network. They become your distribution amplifier, if you will. They become a methodology by which you can even do free running. And this, quite frankly, is a lot of times how we set up our interops in actually environment. So sometimes we don't have the access to a tech, and we'll actually run one of the switches in PTP Grandmaster mode. So I want to give that sense of that. Now, what comes up quite a bit is, does this scale? It's the first question. The answer is yes. We've done a lot of scalability testing in the 32 and F80 group. We've scaled these to around a couple of thousand endpoints per switch. We're going to get better. We'll probably get to about 4,000 here in about another 6 months or so. But the other interesting thing is, let's say we're talking about Oslo and what's the other? Bergen. Let's say this was split in half. Okay, where do you put your PTP Grandmaster? Both answers are right. You could put them both on one side or split them. Okay, the hard part is if you have a split network and you're dancing to different beats and you put them together, then what happens? So you want to think about failover. You want to think about recombining. The other interesting thing to look at is, and this is the third question that comes up, what if this is a contribution feed? Whose PTP is it? Which beat of the drum are we dancing to? So what you want to do is, if you have a contribution feed at the edge and they've got their own PTP Grandmaster, is split that. Let them just send you the traffic and then combine it and time it as it comes into the network, just like you do with SDI today. Was that okay? Are you guys still with me? This is kind of deep stuff, so I want to make sure I'm not going too deep. Chin. Oh, he needs the clicker.
So this is just a quick list of the number of vendors that we had to work with. It's not by any means exhaustive. And this list.
Wait, what's that thing on the top there?
I have an application with the switches too. So
oh yeah, okay. So we obviously, yeah, it's not in alphabetical order. If it was, yeah, anyway, never mind.
It'll be close to the top too.
Well, anyway, so at least it works. They pass packets, and anyway.
Yeah.
Oh, ish.
Yeah. So in this case, orchestration too is really important.
Extra orchestration, yes. Really
right. So basically, what we had is a mixed vendor environment. So it was kind of difficult to get them all marching to the same tune. One thing that we of course always note is that the audio system tends to have to be on their own island. So it's running across the SDN network, but with point-to-point circuits such that every device can see every other device in the layer 2 network. All right. So it was the one give me that we had to do in order to get all their stuff working.
Because the Ravenna and Dantes are all built upon L2 today. That's the whole point. Now, we are working with them to actually get them to L3. That's some work in progress that we're hoping that Rick can probably help us with. Yeah.
So our contribution, Navion's contribution is really the orchestration software itself, some leaf switches, and processing units. So one of the things that we wanted to do was kind of offload some of the audio processing right at the edge, and that in itself has its own complexity. So each of these cards, for example, can take in multiple SDI videos, output multiple SDI output videos. But the SDIs can also come in as DAS6 with AES67 streams. So if you think about it, a single card, 4 cards per 1 RU, a single card is essentially a 192 by 192 audio router. It's massive complexity. How do you actually contain and route all this traffic? So what they want, they take the easy way out. All the 8 monos, stuff in one AES67, do it right at the edge, send it to the audio router, and let the audio router handle it, right? So even with this combination, there's a little slide that talks about what the scale of the deployment is right now. I'll leave that number to the end. But the overall design. So what we had is a fully redundant spine leaf in both Bergen and in Oslo. The green switches here, these switches are all open flow switches. So it's actually a mixed use environment. These switches are right at the edge on the leaf itself are open flow switches. The purple switches are Cisco switches.
Yeah, it's okay.
These are actually configured using netconf. While we have ASR9Ks and Nexus 7000s, these are existing IP circuits that it already had between the two facilities.
So OpenFlow and netconf and the things we're talking about, it just means to programmatically program the flows into the switch, right? Because what we're not doing is not doing the IGMP stuff. We're actually literally saying you can go down this link.
Right. So one caveat here is that there is no traditional multicast here, right? So this network is not self-routable. If you plug in a device right now, this network will not recognize it as a valid device. It will not transmit. You can't plug in any device and automatically receive if you try to do IGMP join, because IGMP joins don't exist in this system at all. And there is a reason why we do it this way. There are two schools of thought. Isn't this? No.
Yeah, it's a couple more slides.
So there are two schools of thought. One is I want it as close to an SDI network as possible. I want it to be as very, very stable, fixed routes, traffic managed. And the other school of thought is totally dynamic, right? I want my flows to come in and out at will, and I want to be able to send traffic and receive it anytime I want. So both methods have their pros and cons. Okay, so when we go with a fixed network like this, we say it's fixed because if you want to contribute or you want to put a signal into the system, you actually have to tell the system that this particular stream is authorized, that it can be recognized, and that it should be transmitted. If not, by default, every single flow in the system is automatically dropped.
So security is built in.
Yeah, so absolutely. So security is by default built in, because if the stream is not recognized, first action is always dropped. So from a orchestration perspective, what we have is the cloud, or the SDN network, contributed by OpenFlow switches and standard Cisco switches. We have a SDN orchestrator that speaks 2 different languages, that writes the instruction set into the switches directly for routing. And we have Ember Plus, a northbound interface, basically to interface with the broadcast control system. So the user only comes in, looks at VSM. It has a whole plethora of interfaces to go to different broadcast control interfaces. So it could be a panel, it can be literally a web app, comes in the system, and the routes are automatically created.
Yeah, what's interesting about this, though, this is all standards-based stuff. This is things that have been out there. OpenFlow has been out there for a number of years, at least 10 years. netconf Yang, your OpenConfig as well. That's all stuff that's coming up. We're going to talk a little bit more about that. That's literally where the industry is going to. Google's doing a big push in netconf Yang right now.
Yeah. So in the other Arista application that we have, we are using OpenConfig and in place of Cisco.
So multicast, and I know this is all dry material. This is all stuff that I live and breathe. It's always a network issue, right? So that I have to know how to troubleshoot it too. So multicast, broadcast, and unicast. So these are terms that you have to get your head around sometimes when we're talking about this. So broadcast is much like I'm talking right now, and whether you want to hear it or not, you're hearing it. That's broadcast. It's like, I was going to say a joke, but we're recording and I have to be quiet. Anyway, I was going to say when I go home and I'm talking, I just spew it out. That's more of a broadcast, and she doesn't receive it, she turns it off. So that should be more like a multicast, which is multicast as I'm saying it, but those of you who choose to tune in can tune into it. Unicast is 1-to-1. We're talking, okay? That's 1-to-1. So broadcast, everybody gets it. Unicast 1-to-1, and then multicast 1-to-many. Now, when you're doing multicast, it's interesting because I can sit out here and I'm here, I'm sending all this traffic, and the video is just going like a playout system. But if nobody wants it, you don't have to receive it. So that's what multicast does. So when we're doing this, and the reason we chose multicast from a 2110 perspective is we want that have that flexibility. We want to have that flexibility just like an SDI router, where we have something plumbed into an input and you can choose whatever output you want. So we have something called a source specific, which means I'm going to choose a multicast address, 192.168.0.100, but I want it from this one. Here's the analog I use. There's somebody on the corner. I come from Southern California. There's always somebody on the corner selling oranges. I don't know why there's so many orange dealers, but there are, okay, off the off ramps and everything else. Well, I don't want the oranges off of this off ramp. I want the oranges off of that off ramp. So that's what they call specific. I want it off the oranges from Tara sitting over here or Mark sitting over there. So that's source specific, okay? ASM or any means I'm just going to buy oranges. I don't care who they're from. Okay, so that's called any. And that's good when you have regional play out. So if you got something on the East Coast or West Coast, you plumb that system and you say, I'm going to get multicast, and I don't care who it comes from. So that's what they call ASM. You have that option as well from a multicast perspective. From an SDN perspective, it's not about this join leave thing. It's very specific. If Chin goes, okay, Robert, you're going to get this traffic, you get that traffic.
So the goal of a system like this, and okay, so in this particular deployment for TB2, what we ended up doing is creating a whole bunch of static endpoints. So what does that mean? That means that the transmitters are always transmitting or contributing a stream into the network at a fixed multicast address. Those multicast addresses are pre-assigned. And likewise, at the receivers are always listening. It says, give me this multicast address, I want it now. And what the system does is that the system automatically checks and says, is there a connection that exists between this static endpoint to this static endpoint? If it exists, I push the instructions in here on the switch in the MAC address, the routing table, and say that if you see a MAC address here, an IP address from this stream that matches, forward it. And I want you to forward it to a specific port. And we do this for every single stream, input, output, input, output, input, output. So by doing this, in a scenario such as this, if I have multiple paths from one source to a destination, I do the shortest path first. I basically figure out what the the least cost is to get from my source to my destination. And in this particular hop is one leaf and one spine and one leaf. But if you're going from Oslo to Bergen, it's actually multiple leaves and spine switches that you need to contend to.
So it's kind of like Waze in a way, right? So you're actually picking the right path, the shortest path, and if you happen to have congestion, you go around it.
Oh, actually, I highly disagree with that. Waze has sent me down the wrong path so many times.
Oh, I think Waze is sponsored by some real estate companies because I go by open houses all the time. I'm not sure what that is.
Yeah. No,
it's not a routing protocol at all.
There's no routing protocol. It doesn't exist.
It's the mathematical models built into the video iPath. And what's interesting about this, and I don't mean to steal, the thunder here, but what's interesting about the video iPath, it's SDI and IP and IP to SDI and IP to IP and SDI to IP. So it's like it's anything. So if you happen to have an on-ramp that's SDI and that's your available bandwidth, it'll actually use that, the SDI path, or the IP path if it's IP to IP. Right, so it knows about the gateways, it knows about the whole mathematical model and all capabilities from point A to point B. So when you're actually defining that matrix of source destinations, you're defining what the capabilities are in between as well. So it's a full mathematical model around that. So if you happen to have another path that's non-optimized, not shortest path first, it might use that as well, just because you have available bandwidth. So from a networking guy, it's more like an ATM network.
So the other thing is that you worry, right? What we have here, right, in the input to the switches is that it's actually ingress rate policing. So not only do we define what path it takes and whether it can go or not, if we say that stream is allowed to go enter the network, we also check for what's the bandwidth is taking up, right? So you actually reach a point where your connection profiles requires things like, is this a MPEG 4 at 30 megabits per second, JPEG 2000 at 200? Is this a HD circuit? Is it 3G or is it 4K? Because if you don't and you just let it send as a connection, this system can get overloaded very quickly. So you actually have to do ingress rate policing on every single port that a stream is allowed entry into the system.
Because it's doing the mathematical model to know how much to decrement on the interlinks.
Right. So what do we deliver here, right? So we deliver innate security from a flow perspective, right? You cannot contribute any flow you want, so there's no DNS. So there's no denial of service type attacks. no one can come in and steal content unless they physically replace it and try to mimic the device's IP and MAC address. So things like that. There's stream resilience because we can do automatic route failovers. In one of our designs, the orchestration system actually looks at like a 10+4 encoder failover system, for example, that checks the individual behavior of the encoders and switches to another device. So it's kind of customizable from that perspective. One thing that we're doing here is, if you focus on this, is fast and clean switching. Because all the flows are statically configured, there is no join delay. There's no resynchronization delay when you try to change your profile. And we add an additional thing. We add something we call net or driverless deployment. So net network address translation is essentially changing the IP addresses on the fly. Now, why do we do this? We have a bunch of IP fixed multicast addresses that is trying to transmit, and these are the endpoints that's trying to receive. So we heard, okay, we block traffic by default. So if this switch doesn't have a rule inside here that passes 239.0.0.1, it's just going to drop it. So in this case, it drops 239.221. So that's its default behavior. So once we pass it through the system, if the destination device is looking for 230.222, what happens? It's receiving an incorrect multicast address. So what the system does, is a net right at the egress port. It converts them out, it rewrites the IP address on the fly. So this lends itself to an environment that you're essentially looking at a
single stream. It looks like a single stream. So when you actually, it's source-based switching.
Right, exactly. And it's basically an SDI router at this point, right? Inputs and outputs. But all we're doing is we're leveraging IP technology and switching to actually provide this capability. So is this, does it have unlimited capacity? Of course, no. There are limitations to this. So switches like this, for example, in doing this net, is something like 2,000 individual streams. Each stream can be replicated, I think, 288 times. So this isn't really for really high density, low rate stream switching. But in this case, it lends itself very well to this application. So the other thing that this really works well for is that if you today have to add an external stream, you don't have to write a driver. I mean, if we had ISO 4, ISO 5 ready, that wouldn't be a problem. But since not everyone has the support for it today, you can actually contribute any stream you want into the network and have it exit anywhere in the network by creating this virtual endpoints and making these connections on the fly.
So obviously we've been talking about IP addresses. This is new for a lot of people. We know we're going to do some more training classes around this and hopefully have some more online things as well. Because multicast is a bit terse. You have to get your head around unicast as well. Yep.
Limiting ourselves to that with every other sort of area of network going to IP6.
Are we limiting it? No.
So the question was, are we limiting ourselves to IPv4 or will we support IPv6 going forward in this kind of environment?
Yeah, the answer is yes. Are we there now? No. So this is something we want to do from a protocol perspective, but we want to test it. What's interesting about how we've approached this, and this is actually thanks to the VSF and SMPTE and JT&M and AMWA and AIMS and everybody getting together, is before we actually finalize the standard, we tested. And we actually found out some stuff, and we found out with PTP, for example. I'll give you one. So we came out with a 2059.2 profile, and we put it out there, and then we tested it. And one of the things with PTP, with IEEE 1588, it says, when I'm going to send a management message, you have to respond back. Wait a second. So if I send a management message to everybody in this room, and then you respond back, and then you all hear that, and then you respond to the management message, you you just get a denial of service like right there, right? Because it's a response, and everybody responds. You go n times n minus 1 times the responses, and your network just melts out. So we go, ooh, that's not a good thing. So what we've done in all this, before we get to the V6, we're going to make sure that it works in V4 and it scales, and then we're going to go to V6. Does it make sense? So it was a longer answer than you wanted, but I want to give you a sense that this stuff is real and we're testing it, and we're making sure that before we get out there and in the wild that we know that it works. At the last interop, can I say how many people? I can say how many. Yeah, we could. We had about 180 odd devices and about 100, almost 100. 62 companies, yeah, and so 62 companies, and we actually had about 14 racks full of equipment, not quite full, that we had to set up in a day, by the way. So there's more and more. In fact, you're going to see at the IP Showcase at IBC, you're going to see a bunch more. We have about 12 racks worth of equipment, and we were even thinking about this is getting so just standard, if you will. Do we really need to show interop anymore? What we want to do is work on the next stuff, because I think we're going to get to the 200 mark here pretty quick. So the adoption's on the uptake. It's now what we're going to do next. So the other things we're working on that Brad's actually leading up is the rest of the stuff, the registration discovery, which is very, very much interesting. It's where we're going next. And also people keep talking about, we got the uncompressed, we're going to focus on compressed as well. That was a lot of information that I just spewed out. Not trying to impress you, I'm just trying to get you the information. Because I know you're all going to go back and re-listen to this afterwards, right? Yeah. Okay. Question over here.
And I don't know if you're going to get to this. I don't know if you're going to get to this later, or I don't want to steal thunder, but when we were SDI, bandwidth was easy. I had one wire, I had one signal, not a problem. Now we're IP. Now I have these sources go up here. Well, wait, I can have these 20 go through this router. I have a failure. This is a nightmare for figuring out. I don't know how you would ever figure out how I'm not going to choke any individual line. And when somebody comes up and, we got a couple new devices, we're just going to add them onto this router because oh my God, how do we do this?
Schedule it. So it's one thing to know something you have now. It's another thing to predict what I need in the future. And by the way, I need to bring this on for test. And by the way, I want to test this playout system.
And by the way, no, you can repeat it. Future could be tomorrow.
If future was now, and then you go, okay, and now I want to go mixed mode. I'm going to do standard F, HD, and UHD, and then God forbid, yeah, I know, yeah, right. And you go, holy smokes, how do I do that? So this is where the broadcast controller literally comes into play.
Right. So for every path that we make, we also create a service chain for monitoring. So we actually monitor the end devices and the switch, including link up, down, and possibility of even looking at bandwidth utilization per port. So that's the monitoring piece, right? But the actual scheduling piece is also important, right?
And I assume automatic, it's going to monitor and say you hit the 70% threshold or something.
Yes, and in addition to that, you can actually set weights on the individual links. So one use case, for example, is I have a link that is 100 kilometers in distance, but it's only 2 hops. But I have another link that has 3 hops, but the distance is only 10 kilometers. Now, if I take the shortest path first, I'm always going to take that longer route, even though the latency might be a little bit tiny, a little bit longer. So you can actually weigh the system and tell the system, hey, this particular link or this particular path, use this at a lower priority. So you only use it when it's run out of bandwidth on the other locations. So there's a lot of configuration that you can do to get the system to what you need to do. But fundamentally, if you are using this at 90% bandwidth, it will warn you, first thing. Second thing, if you try to run, if this is 10 gigs and running 9 gigs, you try to launch a HD in there at 1.6 gigabits per second, that's it, at 22.2-6, it's going to block it immediately. It's going to tell you, hey, you can't send it over because you have insufficient bandwidth.
Now, the con on that is the fact that you didn't get the feed. The pro is that you didn't get the feed.
But you know that you didn't get the feed.
And I'll use the real world scenario. If you're a news agency, CNN, election outcomes. Oh my God, all of a sudden everything was just pushed. So what you had during normal operation is now gone. Just throw it out the window. You don't know what's going to happen.
So this is where we hope that the scheduling and planning operationally works. That you know that you're going to do this, you're going to contribute it. So this system allows you to schedule in advance 2 years. So you can plan for it. Now, I'm not saying that you need to use it up to 90% capacity. We never advise any of our customers to use 90% or approach it. You can in a pinch, but you will always have events that needs to come up.
I would say you can't use over 40%.
Well, that's where either the green, blue, or what's your redundant paths. So we were talking about that. How much bandwidth do you have available to you in total? And then what's your failure domains? What do you anticipate? Okay, let me stop right there. What do you anticipate to fail? Nothing, right? but what could fail? So you have to figure out what that could be too. And by the way, over time you go, okay, my failures could be on the camera or connection or something like that. So you learn over time about what that could be.
But like with power, you have redundant power. You would never drop more than 40% off each leg in case that one leg dies.
Well, this is where they're getting the green, blue, and the redundancy. Yeah, absolutely.
So
Wait,
every
you
single
did?
switch is
Okay.
dual horn here. There's the dual leaf and dual spine switches. So by definition, you already get a 50% redundancy there. So when they first started this application, they had about 1,000 inputs and 1,000 outputs. By this year, little more than a year later, they're up to 3,000 by 3,455. They're adding new services. They're adding more. They're forecasting this to go to 10K by 10K by 2019. So the complexity just keeps on growing and growing and growing at this point. So the network architecture, the orchestration tool, all the devices, needs to be able to scale up, right? So fundamental choices that need to be made from the start will help them grow or will cripple them, right? So
Unlike SDI, which is either in or out, this is a network switch. So in, out, we don't care. We're just plumbing it in, and one device could be both, input and output. So you actually get a double, if you will, from the bandwidth perspective right out of the bag, because you can be a transmitter, receiver, or whatever the device happens to be at that point in time. So if you have a flexible device with the video iPath functions, then you could actually be an input at one point and then an output at another. So which is good.
Which is kind of funny here. So if I have a gateway device that sits right at the switch, and it's bidirectional, this system allows me to actually turn it around locally right at the switch port. It doesn't have to go anywhere else and come back again. So this, by the default, gives you true bidirectional connectivity everywhere in the system.
Oh, there's a question that came in on the web real quick. So the question is, and we won't identify who it was, great presentation, we love it, where can we find out more? Oh, that's not it? That's not the question? Oh, okay. Can you guys talk, no, okay. How do you deal with a failed device that is set to one IP address and replaced with a new one without IP setting? Do you use MAC address or device ID? How do you actually do the change?
So you use MAC address, so if that device fails, or if you plug in a different system, it automatically discovers the like-for-like system and pushes the configs to it directly, right? So those devices get configured with the broken devices' IP addresses. So again, in this environment, this device can be swapped out for a like device, and you can choose to filter only on the IP addresses. I mean, if you want a highly secure system, you can go much further and do MAC address filtering, IP address filtering, UDP filtering, VLANs, or you're using this environment. The simplest model is just to key on the the destination multicast address.
Okay, hopefully that answered the question. Okay, so here's one of my slides. Little trivia, little fun facts here. So 720p 5994 at 10-bit, we're talking about per 10 gig interface, about 7. We traditionally do 6, okay, on a single 10 gig interface, uncompressed. 1080i 5994 on the 10 gig interface, 6 streams. And then when we get it up to a little bit higher bit rate here, a little bit higher, 1080p 5994, then we're actually at 3 per 10 gig interface. As you can see, mathematically, whew, that's a lot of bandwidth. Okay, what we didn't do was we showed you 10, 40, 100, 25 gig. 25 is the new 10. Okay, that's okay. And I'm saying 50 is the new 30. That's just for me. Again, I got to be careful with the jokes. So if you're looking at a switch architecture, look at 25 gig, because you're going to actually get more throughput and capability out of it. And I don't want to say future-proof, or close to future-proof. 100 gig, and your traditional switches these days, from a Moore's law perspective, we're looking at on a single chip, single ASIC, single network processor, 32 ports of 100 gig. 32 ports, 100 gig, single chip. Very fast. We're announcing here, Arista and everybody else, by the way, 400 gig on a single chip, 32 ports, 400 gig coming out soon. So we were talking about how much bandwidth do you need. Well, you could actually do this on a single type of device like this, 400 gig. It's going to be a little bit bigger in terms of form factor goes as the QSFP. So we're chasing Moore's law here, giving more bandwidth to you, because we know uncompressed is what you're going to be doing in your broadcast facility, and we want to make sure that it runs fast. Single chip, 32 ports, 400 gig each. That's a lot. No. Oh, nanoseconds. Okay, I have to receive the whole packet or start to receive it and either do a cut through. So it's literally the serialization from point A to point B, and then for me to actually switch it out. So we're talking nanoseconds. That's a chip. It's on a single chip. Then you're serializing out, and if it's a cut through, it's literally receiving it in. I take a look at the MAC address and I do it out. Now what you have to be cognizant of, if you're changing speed, it's like on the freeway when you're going from a high speed to a low speed. That's what they call store and forward. I have to get the whole packet, and then I send it out. Yeah.
No, okay, no, not in the world of digital. Okay, you've got buffering, not like old analog where everything matters.
Okay. Good. All right. So that's a tagline, by the way. That'll be the new bumper sticker for IBC next year. Nanoseconds matter. Or maybe that's just for me. I don't know. Good. All right.
Yeah, so they went live in August 2017. This is a nice part of the studio, but when they moved in, they were on picnic tables, right? I mean, they weren't really ready for the move, but they reached a point where they said, okay, we just had to go live. I mean, everybody was crossing their fingers at the point. But thank goodness, everything went well. So it's an ongoing process for TV2. It's not something like they said, I'm going to build it one time, I'm going to forget about it. If you saw from the earlier slide, the sources and destinations tripled. We expect it to go tenfold from its original design in about 2 years from where they actually started the deployment. So the next steps for TV2, they kept on telling us we need to go 2110, we need to go NMOS in the summer. And when we came down to doing it, and they said, maybe not, right? Because they started seeing all the problems. Not all the vendors were ready.
Oh, challenges. No. Opportunities.
Correct. That is right.
Opportunities, yes.
So they've kind of placed this on hold. And what they said is that everything needs to come in the lab. Every vendor that's going to play a part in this needs to come in. Everything's tested first before we actually pull the trigger and launch this. And I think that's the best way to do this going forward. I mean, they have a stable working system. It works for what they need to do. Why rock the boat right now? But it is an active environment where they are testing this on the fly.
Now, there's an interesting thing here, and Rick can talk to you about this for days, is we have the ability to actually mix now, right? 2022-6, 2110, right? Okay. So that was something we actually worked on. In fact, I don't want to say it was an afterthought, but we had to make sure that one worked and the other worked and they both worked well, and then make sure they work well together. Okay, and that's the whole point of these standards. But now, by the way, I don't think the 2110s are done. We're going to continue to evolve through this. We've got another one with multi-link that's coming up and more. So as we learn more about what people want and what the manufacturers can do, we're going to come out with more and more standards to evolve this as well. Another thing we're working on is compression. So how to work with compression in this type of workload as well. With that, holy smokes, that was a lot in a short period of time. Hopefully, oh, there's another question. You want to read it?
Yeah, is it okay? So we have 2 more questions. So can you go over boundary clocks?
Can you, as in hop over or repeat? Explain. Okay, let me show you no boundary. A network without borders. Oh, that was, okay, sorry. Trump fans? No, kidding. Okay, build the wall. All right, so I was a comedian for 10 years. And so there's so many jokes in my head. So when you see me cringe and do the face, you know I'm holding back like 20 jokes. Too many HR violations in one day, and this is being recorded. Yes, and Luann's cringing right now. So the question was about boundary clocks. Okay, we were talking about multicast and PTP. So when you're talking about your SPG 8000A and it's sending out there, it's spewing out this traffic. multicast. Like we were talking about, got oranges on the corner. Okay, everybody want oranges. Everybody want PTP. Nobody wants PTP around here. Why? So PTP is a multicast. It actually is being spewed out here, and you have these devices out here, the receivers that actually subscribe. Or in an SDN world, it's pushed out to it. You must have PTP. Here you go. Eat your peas. Here you go. Eat your broccoli. Here you go. So again, I get to get this stuff out of my system. Thank you. So in a boundary clock less, it's all multicast here. Okay. Or in an SDN, it's like that. So boundary clock allows the switches, and this is on a switch vendor basis, and it's even sometimes different code. Boundary clock on the switches takes that, and it becomes what we call a slave. So the PTP grandmaster is the master. The device downstream is the slave. You can follow these little orange and greens. You've got master, slave, master, slave, master, slave, master, slave, all the way down the end. And it's literally following that chain, master, slave, master, slave, master, slave. So the boundary clock, which runs on the switch, is timed to the grandmaster or the device that's northbound from it. If I'm downstream and he's the grandmaster, I'm the slave. If Chin's down for me, I'm master, he's slave, and so on and so on and so on, just like we were arm in arm. So it goes master, slave, master, slave. What boundary clock allows us to do then is to take that one clock value from the upstream PTP grandmaster, whether it's a switch or the PTP grandmaster itself, and then multiply that. I am now the grandmaster across the entire switch. I'm grandmaster to everybody that's connected to it. Now, the cool thing about that is the SPG 8000A has less number of slaves. It can do more. It can synchronize just to the switches. Okay, so that's pretty much boundary clock in a nutshell. Okay, any?
I've got two for you. And I'm going to jump back to the concept of well, you turn it over. I'm going to go back to the concept that we have plants and we have power, two power chains. We do testing. We do testing every year where hopefully we do with business continuity planning where you'll kill one of the chains and see what dies. Hopefully nothing. We now have systems with so many switches, main and you say redundant and so forth, and traffic which is built and gone here and there, that has any thought been given to the need for, or is there a need for let's do a test on next Thursday. We're going to see what happens if this switch dies or that switch dies, and do we die? Does it affect operation?
So not only, I think you have like 12 questions. That's one. We'll go one by one.
I have two of them, but
you have two?
The big
okay.
one.
Okay. So we'll do hex. Was that zero, or we're going to do a zero base, right?
We'll start with zero.
Okay, zero. So yeah, sorry, geek humor. So has there been any tests? Yes. So for example, in one case, there's something called 2022-7, which is literally the failover. So that's the ability to actually have separate streams, single stream, and fail between the different ones, and actually do the join or through the SDN controller. So the failure analysis and literally knowing what that failure time is. So not only have we done the test, and that's just one piece, by the way. We've also done, this is what we call our dirty hands or interops that we're doing. So it's one thing to have a standard. It's another thing to know how it works in production. Okay. So we come up with a lot of scenarios, and we will literally just set this up, and for weeks on end, we'll go, hey, we're going to test scale. And we'll test scale. PTP grandmaster failover. PTP grandmaster failover at scale. Oh, by the way, we're going to do free run. Oh, by the way, we're going to do a jam. We're going to do a jam across and as we come up with all these different scenarios, even so far as we're going to try and overrun a particular link, and how is that going? Oh, and by the way, we're going to do small buffer, large buffer switches, small buffer. This is all the 2110-21 stuff, small to large, large to small, small to small, large to large, all that testing as well. A lot goes into this.
My question was referring much more to real world. You have this situation. It was what were the two cities, Bergen and Oslo? And they started about 1,000 square.
Sure.
Now they're about 3,000 square plus. You're talking, well, it was designed for 1,000, or you set it up as 1,000, look great. Now people have been adding. Are they going back and saying, what happens if at 3,000 square? What happens if I start losing a switch?
So this is capacity planning as well. I think you'd agree, right?
Yep.
So capacity planning. So what's interesting about what you just asked and how you characterize it is, in this particular case, we're talking about spine leaf. Okay, there could be a monolithic switch, which you have buku bandwidth with. In this case, you're doing kind of tie line management. So if you have an SDN type of controller, it's going to gate you down at the edge and not allow you to give more bandwidth than the network can consume, first off.
I guess my question was more of, and we've seen it with power where someone designs this beautifully. And then next year they find that somebody has come in with a couple new boxes and they plugged it into one chain and they shut off, they ran the test and lights started going out.
Or my favorite is they plug in both redundant powers into the same PDU.
Right. Well, but then
Never
in the
happens.
case here, this complexity is at such a point that unless you're going to go and turn off a switch one at a time and try them all, you really need some very automated software tools that will help you. What would happen if this happened and let you diagnose it?
Or you can actually extrapolate from. So if you do one test scenario and you know it's going to oversubscribe, so that at least you can extrapolate that over, yeah. See, QoS means I'm rate limiting or prioritization, okay? If you rate limit, and I need to give you 2.5 gigs worth of throughput, I need to give you 2.5. Okay, you don't want to cut that down because now you just took part of my stream, which basically you're sending a dirty stream, right? QoS in a prioritization scheme, if, for example, PTP, we always recommend PTP because that's the beat of the drum to be highest priority. But here's what's interesting. If I prioritize one stream over another, I might as well just say, I'm not going to send this other stream, because to have something that's half working in the broadcast industry, that's a failure. You see what I mean? So yeah.
So I get your point, and so the way we set it up is that the individual connections have different profiles, and when you apply the profiles dictate what kind of redundancy is applied. You can actually tell the profile says just apply this, no redundancy. If this fails, it's dead.
Yeah.
Then you can assign another profile to another device that says this needs dual hardware -7. It needs to go path diversity. It needs to do everything. So you can do it that way too. So you have a level of redundancy and failure.
Sorry, I'm gonna ask you a question so you're blue in the face, so.
We're
Priority, is that head in the packet, or how do you prioritize a device like that?
So the pack, we don't prioritize on packets at all. Packets are just packets to us.
Okay.
We actually prioritize based on connections. So a particular device can output two separate streams, and one stream can have a higher priority than the other. But prioritization here means a different thing. It's not QoS. It just means what is its failover characteristics in terms of a failure.
Okay.
So one stream can be no redundancy at all, and the other give me the works, everything. So that's how it's actually done today.
Yeah, exactly. In fact, what he was just talking about is the fact that you could have something that says, this is just a contribution or whatever it happens to be. And in case of oversubscription, that's not allowed on the network, literally, okay?
Can you do that time-based? Let's say an automated schedule. Let's say I'm always rolling on a Flash Studio for some reason.
So a connection.
From 5 o'clock to 12 o'clock.
So the system today doesn't support that.
Okay.
So you can create profiles and schedule the connections in segments. The problem is that it's non-continuous, right? So that will be kind of like the special application.
If I could respond, James, if I could respond one point. If you have a system where at some point somebody's going to be told you can't do this, you have a problem, because you're going to have one really hopped up, angry producer coming against you. So, but when you design a system like this, I think if you have a design that you put up that will sometimes tell somebody you can't do it, I think you failed. I understand, but I think the system design has to allow for everything to work. One last question question one, the other one was 0. And that is, and this may not be in the scope of this topic, but we are now moving to a point where everything we have is a software-based device. And I'll go to the other extreme that I've got my phone that every day says, oh, 7 things updated. And I'm just starting to vision this going, okay, I got a 10,000 square, I got 20,000, I got, oh my God.
Well,
How do we
I'd
handle
rather
updates?
have that and an acknowledgement of that, other than I rolled out an OB truck and nothing's updated. And I knew I had to take the time to actually do that. So, but
But
you're
on my
right, this
phone,
is the
things cut out when
this
it
is the
dies.
software driven world. It really is.
So the question we receive is, who actually does the scheduling? Is this a third-party scheduling system? Is it Schedule or is it Data Miner?
Right.
The scheduling is actually innate in the orchestration tool itself. So there's a scheduling tool, but one thing is missing is billing. So you can schedule it, but you can't send a bill to anyone. So that's what we do with what we've tried to do with Schedule, where they will actually do that. The other thing is that the broadcast control can actually write the connection request to us, so they can be the scheduling tool to us also. So it depends on where you sit within the workflow. If you are more, I would say, if you really want to use VSM, then that's your first choice. You're going to go there to establish all your connections and schedule it. But if you want something that is more application-based, you go to Video iPod.
Yeah, and that whole thing is, this is all about APIs at that point, the ability to consume it as a usable object.
Absolutely.
More questions over here? Okay.
Just a real simple.
No, this is something completely different for me. Queuing for him. I'll talk forever.
This is kind of going backwards. Just in basic terms, in this facility, what kind of bandwidth are we actually talking about? I mean, I noticed J2K, and you talked about some other stuff.
That's a
What
darn
what are
good
they actually
question.
what are they actually pushing, and how much of what? And is it J2K like mathematically lossless? What's
So it's not, so we're talking about the 2110 stuff today. It's all uncompressed. And so we got that one slide that talks about how many streams you can actually do, right? The bandwidth thereof. Go back to the, yeah, that's good. That's good-ish. What we're finding is there's 2 types of devices that I call the gravity effect. Heavy things, very heavy things. One is a multiviewer, okay? Another one is an analytics tool. An analytics tool sits on the network and it just joins all the feeds, because analytics tools are expensive. And sometimes you'll have distributed analytics and sometimes you'll have centralized, and you want to bring that traffic to you. So we're finding that those analytics tools are 100 gig or 200 gig ports or 400 gig ports. Multiviewers right now, the one on the market that I'm thinking of, there's actually 2 on the market that have 200 gigs on it. They're forecast to have 400 gig interfaces on these. Wow. And you're going to have a whole wall of multiviewer. Well, where do you put those things, right? So the bandwidth we're looking at right now is a lot of 100 gig, at least a spine to leaf. Because if you think about that 10 gig link, well, it's only 10 to get to 100, right? If you've got a 48 port 10 gig switch and you've got one 100 gig link, you're oversubscribed.
what I actually meant was what are they actually pushing right now? I mean, all the cameras pushing out 25 megabit HD?
Depends on the camera. Mostly 1.5.
It's all uncompressed, and we use gateways to convert. It's Sony cameras.
Yeah.
So this is the.
Yeah, just a little bit of.
Yeah. So the entire system, it runs on 52 100 gig circuits, from all the leaves to the spines. Then from from also the Bergen is dual 100 gigs, but I think they only use something like 60 gigabits for broadcast traffic. So at some point you can use uncompressed, but when you have too many circuits, it defaults to JPEG 2000. Right. So they are trying to push uncompressed everywhere in the system, and that's a large proportion of it. I mean, the IRDs that comes up that takes the satellite feeds and contributes transport streams, there's only about 10 streams or so within that environment. So that's a very, very, very small percentage. And there is no J2K within the facility. It's only across the 2 cities. No. It's lossy. So we run it at approximately about 120 megabits per second.
Yeah, within 2110, the current approved standards are all for uncompressed. However, we are working on a 2110-22, which will allow for the use of compression. It does not. It's a registry table, so any compression you want, submit it. It goes in the registry table. So we're agnostic as to what type of compression it is. So that's what will happen if you want to use compressed. Going the other direction, we are working on a part 23, which is if it doesn't fit in one transport, you can actually segment your image and break it down into multiple transport streams and send it through multiple ports on a 2110 switch. So that's going,
The same idea.
no, that's easy. Never mind 4K. How about 8K P120 12-bit 4444? Yeah. So 4K simple. 4K 60 is easy.
And we'd be glad to sell you a couple of switches just for that, by the way. You'll need the 400 gig. We had more questions. Do we have another questions on the line first? Okay, we're good. Okay.
So what's that WAN connection? Is it over public internet or is it a dark fiber?
It's like an LTN circuit.
LTN circuit?
Yeah, then there's multiple wavelengths. So, but they only subscribe to 100 gigs between those two
Got it.
locations.
So I've heard a lot about IP over the last few meetings. I haven't heard anything about security or encryption or man-in-the-middle attacks via a WAN network or anything like that.
So yeah. So I mean, in the broadcast domain, I mean, there's already encryption standards available. For example, we are just right now pushing out DVB-CISA. It's basically AES 128 encryption, right? So the problem is that it's intensive, really intensive. You can't really apply this in a compressed domain. What we could do is get everything, uncompressed domain. What you could do is get everything compressed, encrypt it, and then send it over. I mean, that's an option. We've talked about potentially using AES encryption or other security tools from the IT side of the world to do that. But within the facility itself, every facility is prone to it, right? I mean, the problem is not outsiders, but someone coming in and doing something internally, and that's always the problem. How do you actually secure that?
Yeah, so there's a couple of things we're working on from the AMWA side of things for a security standpoint. So we do have some onboarding tools. So we've got Nevion, we've got a bunch of toolkits out there. Body conscious controllers are basically that methodology, that gate, if you will. Okay, because if you can't bring it in, you can't actually use it. Okay, that's one thing. On the AMWA side of things, we're talking about this, and by the way, feel free to join. If you want to participate in this, it's an open forum. Just join AMWA, AIMS, these groups, and have a voice. What we're thinking about doing is kind of an 802.1x approach, and for those that don't know, that's kind of like what you're doing with Wi-Fi, where you do the authentication, you have the encryption, things like that. We're talking about those types of things, but do you want to do that encryption in the PHY at the end? Where do you do the encryption, and do you want to put what they call a supplicant? When you connect to Wi-Fi, you have this thing called a supplicant. Do you want to put a supplicant on the edge? Remember, some of these things are AES 67 devices. There's little audio devices. Some of them are like 10 megabit connections, little tiny, devices, right? So they're not that much in there. How much you put it? In the first case, we were talking about ISO 4 and 5, at least the ISO 4 with the Bonjour type protocols. Some of those guys were just falling over because they couldn't handle it from a memory space perspective, so they had to redo their PHYs. So we don't want to push them. And then we also said, by the way, to be ISO 4, you have to have something called LLDP, Link Layer Discovery Protocol. Basically says, I'm here. And it tells the switch upstream, dude, I'm here. And that caused some little consternation as well. So when we start to ask for even heavier protocols and putting a supplicant on there, and then how do you put certificates out there? And then where do you put your certificate authority in there? It blows people's minds. Do we need to do something like that? Yes. Will we get there? Yes. Are we there now? No. So we're using broadcast controllers or onboarding things from a Skyline data monitor to actually bring things on. That was a long-winded answer, but I want to give you a sense of, yes, we're thinking about this. There's a long way to go, and we kind of know what the chartered course is, and we're also trying to entice other people to come in and join the group to help us work through this. Okay, cool. Other questions? No. Wow. Okay. Okay, feel free, you're gonna have our email addresses at the edge there, at the end. And I'm gonna turn this back over to Bob. Before I do that, thank you, Luann, for coordinating this and getting us all together. And thanks also for the press release. Kudos to you. And Mr. Ackerman for pulling together the 2110. And Brad already left because he tapped out. And by the way, thank all of you for listening to this and participating and being SMPTE members. We need more and more. Get the word out. Let's get some more people to join SMPTE. Bob, back to you.
Thank you.